NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Well, JWST is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful.
Pluto is a far-off and stealthy, more unassuming planet that was once a piece of our nearby planetary system. However, late, groundbreaking declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have carried Pluto back into the spotlight with a stunning discovery. They propose that this cold world is on a potential crash course with Neptune. But how could this happen, and what might be the consequences of such a colossal event? Are we witnessing a fascinating cosmic peculiarity? Or is there more to this impending celestial mishap? Join us as we explore the potential consequences of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a dwarf planet partly because of its peculiar orbit, remains a subject of interest and study in the cosmic community. According to recent estimates by leading scientists, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially dangerous collision between these two celestial bodies, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, straying significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unique is its inclination of 17 degrees to the ecliptic plane. The way Pluto follows its path is far more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's orbit. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to understand its unusual path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and elongated shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is a testament to the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, like Pluto, Neptune, and the Sun, move and interact with one another through gravity. It's akin to predicting their movements based on their starting positions and gravitational interactions. For Pluto, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex way. The terms azimuthal libration and degree libration, along with the VZK oscillation, are crucial in this puzzle. According to astrophysicists, what keeps all planets in their orbits is azimuthal libration. For Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is vital in preventing their orbits from intersecting. Degree libration, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, adding an extra layer of protection from potential collisions. Another important aspect is the VZK oscillation, named after three scientists, Vashilov, Zotov, and Krivov, who studied how objects move in space. It describes how three space objects like Pluto, Neptune, and the Sun gravitationally interact. This gravitational pull influences their movements. For Pluto, the VZK oscillation helps explain why its orbit around the Sun is so unusual. Despite its seemingly erratic orbit, this oscillation ensures that Pluto moves smoothly over long periods. The VZK oscillation demonstrates that, although things in space may appear chaotic and unpredictable, certain patterns and forces maintain order. All these factors help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or veer off course. This three-body problem is key to understanding how orbits evolve due to the interactions between celestial objects. Studying this not only helps us learn about Pluto and our solar system but also distant planets and their stars. Numerical simulations in the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is quite chaotic. Minor deviations in initial conditions can lead to significant changes over millennia. However, the remarkable properties of Pluto's orbit have been found to maintain stability over incredibly long time scales, mitigating chaos. Later computational models have helped us understand how the giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only player in this. Jupiter's gravity also plays a crucial role in stabilizing Pluto's motion, as does Saturn. These reproductions show that Jupiter's gravity alone is sufficiently able to guarantee Pluto stays on a steady path for quite a while, even for many years. So perhaps Neptune, Jupiter, and Saturn are cooperating to ensure Pluto continues to move safely in space without running into trouble. These characteristics are fundamental for maintaining order and stability in space. Without these elements, the solar system, as we know it, would be a much more chaotic place. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a chain reaction with other celestial bodies. For Pluto, especially with discussions about it potentially colliding with Neptune in the future, understanding its orbit is crucial. This provides a clearer picture of the dynamic nature of the solar system. The case of Pluto shows that even the most seemingly unstable orbits can reach a state of harmony through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the peculiar nature of celestial bodies, and Pluto's orbit is a perfect example of this oddity. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly illustrated with Pluto. This means that even slight changes in the dwarf planet's position or speed can drastically alter its long-term orbit. Using computational models has been immensely helpful for scientists in figuring out how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune pull on each other. By tweaking small details in the simulations, astronomers can see how even tiny changes can make a massive difference in where Pluto ends up. In the late 1980s, these simulations revealed something fascinating about Pluto's orbit. Although it has mechanisms like axial tilt and scope vibration to keep it stable, its orbit can still be unpredictable and chaotic. Starting with just a small difference in Pluto's position or speed can result in a completely different orbit after several years. However, even with this chaos, Pluto's orbit remains stable over extraordinarily long periods, like billions of years. This means that Pluto's journey around the Sun has a kind of order to it, even though it appears chaotic at first. Predicting celestial events, especially when they involve irregular orbits like Pluto's, is a massive challenge. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical models provide valuable tools to understand and predict the future paths of celestial bodies, they also highlight the limitations of our predictive abilities. These models heavily rely on the accuracy of initial conditions, and any small error or distortion can lead to drastically different outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of planetary orbits like Pluto's reminds us of the ever-changing and dynamic nature of the universe. While we've made great strides in understanding space, Pluto's case serves as a humbling reminder of how limited our knowledge of the universe still is. Understanding the gravitational effects of the giant planets on Pluto's orbit provides significant insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly affect the stability and trajectory of other bodies within the system. So, why are prominent astrophysicists recently raising concerns about a potential collision between Pluto and Neptune despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and a major figure in promoting cosmology, offers a fascinating perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's interest in the uncharted realms of space. Tyson's stance on Pluto's reclassification is based on the ever-expanding knowledge of our solar system. He views the reclassification not as a demotion but as a significant adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. The interest in these matters keeps the exploration of space so exciting. However, despite Tyson's optimism, his thoughts on Pluto's possible collision with Neptune paint a more uncertain future. He emphasizes that the orbits of Pluto and Neptune will continue to evolve, driven by forces that are sometimes unpredictable. Interestingly, Tyson also mentions that these uncertainties could potentially lead to Pluto moving closer to Neptune's orbit over the next few million years. Despite this, he remains cautiously optimistic about the likelihood of such a collision. Tyson's analysis suggests that while the chances of such an event occurring are low in the short term, the unpredictable nature of planetary orbits means we cannot completely rule out the possibility of such a collision in the distant future. In addition to Tyson, Michio Kaku, a renowned theoretical physicist, also weighs in on the implications of a potential collision between Pluto and Neptune. Kaku's analysis combines cutting-edge physics with a deep understanding of cosmic evolution. He believes that such a collision, if it were to occur, could have profound implications, not only for Pluto and Neptune but also for our understanding of the universe as a whole. According to Kaku, a Pluto collision could trigger a cascade of other events, potentially even altering the nature of the solar system as we know it. However, Kaku also acknowledges that the likelihood of such a dramatic event happening any time soon is extremely low. He points out that while the orbits of Pluto and Neptune are in close proximity, the vastness of space and the complexities of their orbital dynamics make a collision unlikely in the short term. Nevertheless, the possibility remains a fascinating topic for further study and speculation within the scientific community. In conclusion, the possibility of Pluto colliding with Neptune remains a topic of active debate among astrophysicists. While the mechanisms of their orbits prevent a collision from occurring in the near future, the complexities of celestial mechanics mean we cannot rule out the possibility of such an event in the distant future. The ever-changing nature of planetary orbits reminds us of the dynamic and unpredictable nature of our universe. Whether or not such an event occurs, it serves as a fascinating example of how much we still have to learn about the future of the solar system.